Good evening. Welcome to Eduinfinite maths classes. And as I told you, in the last class, you have done the problems on straight lines. Now, basically, we have got certain things which are left out in this syllabus. But at the same time, you have to practice the sums from previous topics almost in every alternate days. As I told you, the main we will concentrate on calculus, that is differential calculus. And last time on request, I have done something we have done up to function, and we want to revise that portion very quickly. And today, let us start the topic. Let us see rather why calculus is important. What happens if we don't know calculus? Fine. And what are the topics, what are the concepts involved in calculus? Okay, fine. Let us consider the situation. Suppose we have to find the area enclosed by the curve and the x-axis. Suppose I want to know this area, for instance. How do I get it? First of all, let's see, this is on a number line, x-axis. So, we need the concept of numbers, especially number theory, and especially real numbers. And that is why the other name of calculus is real analysis of real numbers. And very loosely speaking, we use the word calculus, okay? Actually, it is real analysis. Now, this is the real number system, so we must have some concept of number theory. And in the very beginning, make this point very clear that in the calculus of class 11 and 12, we will restrict ourselves in the real numbers only. Now, although we have come to know there is complex number also, and real number is a subset of complex number, but that this calculus, this analysis will not allow any complex number to enter into it. Although you know that real numbers are also one kind of complex numbers. Apart from only real numbers, we don't allow anything. You may ask, then there is no calculus for the complex number? Yes, it is there. But we will learn it after a couple of years, not now. For the time being, by calculus, we mean real analysis, and only real numbers are allowed out here. Clear? Second thing, and you know that this is a part of, say, A to B. It is an interval. You know there are three types of intervals. One is open interval. If I use numbers, it will be easier. 2 to 5. It means all the real numbers between 2 and 5, but excluding 2 and including 5. That is, if x is considered to be any number between that, x is greater than 2 and x is less than 5. If we use the sign of inequality. Second is 2, 5. That is, it will include all the numbers between 2 and 5, including 2 and 5. And this is open interval, this is closed interval, and one is half closed or half open interval. Here, x will include 2, exclude 5. Here, it will include 2, but it will exclude 2, but include 5. These are known as half open or half closed intervals. Okay, we must know this is a subset of AB is a subset of real numbers. This concept of set theory is very much involved out here. We must know what is this boundary. Is it a part of a circle? Is it a straight line? Or each and every part of their behaving in different ways? That is also possible. They may be uniform also like this. They may be like this, or it may be like this. In different parts, it's behaving in different way. This is what is known as function. This is what is known as function. The concept of function. Now, what is our plan? How to get? I told you that my idea is to get this area. Now, you know that initially, in the early days, suppose if we look at the villages even nowadays, if you go a little far from the city, you'll find they don't employ any civil engineer to build up a house. The workers, they put their distinct concept to build up the houses and all these things. But when you come to the urban culture, you find that for every single step you have to take the permission from the corporation or municipality that this is our area, this is the plan, and they will decide whether this plan can sustain or not. And there are so many factors. There are civil engineers, there are other engineers also, architects. They will decide what will be how will be the construction and what will be the sustainability of the construction and so on. That is, to measure the area of these four walls, so you don't need calculus. Because in villages, those are building up those who are giving the plan of the house and building up their houses, they don't know calculus. The drivers, those who are driving the car, they do not know calculus. To know what will be the size of the door, how it will be prepared, the carpenters, they don't know the calculus. But they are doing the work very efficiently. My question was not that. My question was, then why should I know calculus? If so many things can be done without calculus, why should I do? Okay, but if we look at the practical situation, say we are driving a car, is it always with uniform speed? There are so many other factors. Friction is there, the air is there, and all these things are controlling the whole situation. And every single moment it will keep on changing. That is known as instantaneous velocity, and all these things are very much there. So, in calculus, we talk about all those moments. How? Say, if I want to find out the area of this thing, I divide it into infinite number of parts, like this. If we look at a single one, yes, it's like a rectangle. It's a rectangle with, sufficient length, but its breadth, if I consider this breadth is very small. So if it is delta x, say for instance, it is fx into dx, fx into dx. That is length into breadth. So the process, and sometimes we have to see whether this thing is there any break in the sense I'm telling you. What is first of all, let's see, what is the length of, or the width of each rectangle? Almost 0. Is it equal to 0? Answer is no. It is something almost tending to 0. Now, you know that The first definition in geometry which we have learned, it was point. What was the definition? Point is something which has got no dimension. It has got position only. Surprisingly, so initially we learned that point has no length, no width, no height. But afterwards we found those points were in there, kept in a particular direction, put them in a particular direction, a line is formed. When those lines are kept one after another, infinite number of lines are kept one after another, a plane is formed. When this plane is kept one after another, a space is formed. That is, we started with point. From the point only we generated the line. We generated the line, from that we generate the plane. From the plane we generate the space. So it is the ultimately we find that from the point everything is being generated. Although initially we learned that it has got no dimension. So what is the correct thing? The point has got everything. Length, almost negligible if we talk about one. Width, same thing. Height, same thing. And that is why you found that when we talk about some element, say iron or aluminium or anything, when we consider good amount of aluminium or iron or whatever, or copper, okay, we get some qualities of that. We can find out, okay, these are the qualities of copper or aluminium or iron. But to know it more, we break it up. We get molecule. When we get the molecule, we get some more information about that particular. And then we again break up atom. We get some more properties. And we break atom, we get electron, proton, neutron. We get much more information. Same thing, when we learned that numbers, they were far. One, there was a gap, two, then three, then four, there was a gap. Even up to integers it was so. But when we found the fractions, immediately I found the gap, the numbers between the two numbers, two integers, two whole numbers. That is rational number. I cannot say these two rational numbers are side by side. No. In between two rational numbers, there will be infinite number of rational numbers. Same argument is applicable when it is real number. I cannot say these two are consecutive real numbers. Between two real numbers, say 1.00001 and 1.00002. Between these two real numbers, there are an infinite number, at least one real numbers, and thereby infinite number of real numbers. That is what is known as dense property. So in this way also, when we try to analyze something, analyze even a particular compound or anything short of that in physics, chemistry also, we break it up into infinite number of parts. Here also we do the same thing with real numbers. And in a poem, Rabindranath also wrote, Khudra khudra balukana bindu bindu jal, gore tule sagor samudra mohakal. So that is the situation. Initially, if we talk them individual existence, they almost do not exist at all. But collectively, if we look at them, they are doing havoc. There's sometimes, as I told you, that from the point that generating the space and all these things. Now, what is the width of each rectangle? Almost zero, but not exactly equal to zero. Now you may raise your point, but it's all the same thing. We will see that when we discuss that. What will be the number of rectangles if we break up into infinite number of rectangles? The number of rectangles tending to infinity, width is tending to zero. So this concept, tending to, Almost, that is not concept of limit. Sometimes, say, I get fx is equal to 1 by x minus 2. And suppose I am talking about this is 1 to 5, for instance. But when x is equal to 2, do I get any corresponding fx value? No, it will not exist. We see that the function is discontinuous at the point x is equal to 2. Or in other words, if we talk about the graph, and if we find a break at some points, these are known as the points of discontinuity. So we have to check whether the function is continuous everywhere or not. So the concept of continuity. Finally, backed by these very, very important concepts, we get the two types. First, breaking up the whole into infinite number of parts. That is what is known as differentiation. And finally, what we have to do? Finally, we have to get the whole area. So we have to sum up those infinite number of parts. That is summation of all those rectangles, all those parts, infinite number of parts. That is known as integration. Summing up and breaking up, integration. So, there are two types of calculus. One is differentiation, one is integration. And in class 11, you will find most of the times it's all about differentiation. Although in physics, you will get some integration problems, especially in motion and all these things. But actually, as I told you that sometimes we learn rather in the initial stage of class 11, what is the differentiation of x to the power 4? 4 will come in front and the power will be reduced by 1. That is dtx of x to the power 4 is 4 into x to the power 3. Look, we can teach this thing even in class 7 also. This particular, to learn this rule, it's not all about calculus. This is not calculus. These are some certain rules which are applied. So from that point of view, I mean, it's very easy. But to understand calculus properly, you can enjoy that subject, you can enjoy the topic, you can enjoy the aesthetics, beauty of the whole topic, that is calculus. Fine. Now, out of these topics, we have already done the number theory. Actually, we have done a little bit extra, that is complex number also, you know. But as I told you, there is no provision of complex number. For complex number, we have got separate type of calculus. Set theory, we have done. And after set theory, I spent 1 or 2 classes, maybe 2 classes. That is, I'm just giving you our journey in brief, which we have done before. I'm not explaining it in total, but let's see. But in between, if you have got any comment or any question, you are always welcome. Now, say, I am starting from set only. Now, in set, although we have done set theory properly, we have done problems on set theory. First of all, actually, we initially took the path of algebra, of set algebra, where we defined set. After that, we came to know how to write a set. Initially, with the help of two methods. One is tabular or roster form, one is set Wheeler's notation. After which we learned certain concepts, certain important terms involved in set theory, like the null set, element, This, that subset, then okay, equal sets, equivalent sets, and many other things we have learned. After which we have learned that the operations of set theory. The first fundamental four operations of set theory, that is union, intersection, difference, and complement. These are the four. And after learning, we reached up to a particular point, and from which I told you there are two paths getting to two very important topics. One is one path, algebra of sets we have learned. There we have learned certain laws of set algebra, idempotent laws, identity laws, then commutativity, associativity, distributive law, De Morgan's law, difference law, absorption law, etc., etc. And then we proved all these laws with the help of either with the help of the Venn diagram. We came to know about the third method to exhibit the sets, that is Venn diagram. Then we have done the logical reasoning with the help of the logic, how to prove the different equality of two sets. With this we have done. And then the second part, in this, first we learn what is an ordered pair. Ordered pair. Ordered pair is A comma B. A is known as the first component or first element or abscissa. B is known as second component or second element or ordinate. And A comma B usually not equal to B comma A unless A is equal to B. And by chance, if A comma B is equal to C comma D, immediately we draw the conclusion that A is equal to C and B is equal to D. After which we learn the fifth operation of sets. Up to this point, we have learned that operations union, intersection, difference, and complement. And I have given complement in the separate part of this time because these are known as binary operation. Binary operation means to define these operations, we need to involve at least two elements. But out here, A complement itself is defined, but A union, A intersection, A difference will not define anything unless I introduce the second set B. Fine. Then we involve the second operation, the fifth operation, which is known as, now some of these operations, as I know, we discussed whether they are commutative or associative or distributive or not. Now we learn Cartesian product. Of two sets, and the restriction was the sets, both the sets has to be non-empty sets. Then we define A cross B is equal to set of ordered pairs X comma Y such that X is coming from A and Y is coming from B. Cartesian product of two sets is a set of ordered pairs of X comma Y. X is coming from A and Y is coming from B. So the elements in that Cartesian product, all those elements are not like ordinary elements. They are individually ordered pairs. And this ordered pair, we made it first when we were in class 9 or maybe in class 8. We came to know that we have to exhibit a point with the help of that ordered pair A comma B. Clear? Fine. Then we also came to know that as these are producing the set of ordered pairs, can anyone tell me, here we learned another method of representing sets. Earlier we have learned roster or tabular form, then set builders form, and in fact we learned it in class 6 or 7. In class say maybe 11 or maybe in that level only, 7, 8 level, we learned another thing which is known as Venn diagram, and also we practice that Venn diagram in a larger scale, larger difficulty level in class 11. Here, after learning this, I told you there is another way to represent the set. What is that presentation? Can anyone tell me? Can you recall that here at this point of time, we learned another way to represent a set. What is that method by which we exhibit? What's possible thing? Your answer will be wrong, nothing more than that. Anyone wants to try? Anyone? Okay, Shumeda.
Yes.
What was that?
Sir, set of ordered pairs.
Set of ordered pairs. No. Set of ordered pairs is itself it's a representation by Rashtra form. If we just take the set of ordered pairs and exhibit them, that is itself the Cartesian product. There is a special name. Molinakshi?
Sorry, I don't remember.
Forgot. Dipanjan? Jishnu?
Yes, sir.
Can you recall that? First question is very simple. Can you recall that? Answer is either yes or no. The method was known as lattice diagram. Okay, let me ask you one question. Do you think that you should practice a little bit of Cartesian product? That you just forgot the thing. If you feel that if it is so, then it's not the question of revision, which is the first. We will do something more. It may so happen as at that particular point of time, as you thought, oh, this is not in the matter, why Sir is doing that. In that case, we can practice little bit. We can elaborate the topic. I mean, we can explain it something more. Should I do that? Shall I discuss the topic once more? That is, okay. So Cartesian product. What is Cartesian product? I have already given you A cross B, so that both of them are non-empty. Now, why non-empty? I will explain it immediately of X, Y, such that X belongs to A and Y belongs to B. If I consider A set A to be 2, 3, 5, and set B to be 1, 2, 4, then A cross B, all possible ordered pairs was the first component to come from the first set. That is 2, 1, 2, 2, 2, 4, 3, 1, 3, 2, 3, 4. Finally, 5, 1, 5, 2, 5, 4. Now, certain observations. First of all, I mentioned that both the sets will be non-empty sets. If one of them is empty, then the ordered pair cannot be formed. Because the second set or first set, if one of them be empty, then there's either second element, there will be no contribution from the second set, or if the first set is empty or null set, then there will be no contribution. Nothing from a 1 doesn't make any sense. It will not be an ordered pair. Number 1. Number two, total number of elements you just find it is still 1. It is 9 out here. That is, if it is 4 and if it is 2, total number of elements, then A cross B will contain 4 into 2, 8 elements. If it is 3, it is 3, 3 into 3, 9. So, if n of A, cardinal number of elements be P, and n of B is equal to Q, then n of A cross B will be P into Q. Now, can you tell me whether this operation cross product, cross P, A cross B, or the Cartesian product of A and B, is it commutative or not? Is it commutative or not? Commutative means if we interchange the place, I mean A cross B and B cross A, will they produce the same set or not?
No, sir.
No, very good. No, so this product is not a commutative. Just like ordinary addition, 2 plus 3 is equal to 3 plus 2, it is commutative. Multiplication, ordinary multiplication is commutative. But subtraction and divisions, they are not commutative. Is it okay? Fine. Another contribution, as I told you, you have heard this particular name, Cartesian, in some other topics of mathematics. What was that? It was just few days back. We started, and in the last class also I know that we have done the problems of straight lines with Shantanu sir. He was discussing probably the problems from straight lines, and that geometry is known as Cartesian geometry. Why Cartesian? Because real number into real number, they are producing that whole Cartesian plane. Talk about any point in the plane, A comma B. A is coming from this real number, B is coming from this real numbers. So that whole Cartesian plane is generated by the Cartesian product of real numbers with real numbers. And that is the greatest contribution of Cartesian product. Is it clear? Now, from the Cartesian product A cross B, from this Cartesian product, I try to generate some subsets. But before that, let me give you one or two problems. Okay, just write it down. If capital A is equal to 1, 2, 3, that's it. capital B is equal to 4 comma 5, and set C is 5 comma 6. Set A is 1 2 3, set B is 4 5, and set C is 5 comma 6. Then verify that A cross B into C, B union C, is equal to A cross B union A cross C. Second, A cross B intersection C is equal to A cross B intersection A cross C. And finally, A cross B difference C is equal to A cross B difference A cross C. Set A, set B, and set C, these are given to you. Shall I write the sets or it's okay?
Sir, it's okay.
Okay. So let us try. First, the left-hand side of this sum, A cross A means 1, 2, 3. Cross B union C, 4, 5, 6. What do I get? 1, 4, 1, 5. This is 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5. This is etc. 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 A cross B. A cross B. This is 1, 4. This is the right hand side. 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. Intersection. Intersection. Sorry, union. I am doing this one. A cross C. 1, 5, 1, 6. 2, 5, 2, 6. 3, 5, 3, 6. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. There are certain elements which are common. That is 3, 5 is common. 3, 5 is common. Another thing, 1, 5 is common. 1, 5 is common. And if you don't repeat them, it is 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, and 3, 4, 3, 5, 3, 6. Exactly same. So this is correct. Can you do the other two sums with this with the help of that?
Yes, sir.
So can I shift to the next topic?
Yes, sir.
Very good. Can you recall those set theory in the sense that algebra of sets, or you want to practice few sums with the help of that? Say, with the help of law of algebra of sets, A difference B into B difference A, A difference B union B difference A, union B difference A is equal to A union B difference A intersection B. You do it with the help of both Venn diagram as well as law of algebra of sets. First try it, then definitely I am with you. If we talk about Venn diagram, I don't think there is much about to do. That is, there are two sets. First, second, I need 1, 2, then 3. Then 3. For this, 1 for this, 1 for that, 1 for difference. That is also 3. But one thing is good that I don't have the third set. Only A and B are there. A, B, A, B, A, B, A, B, A, B, A, B. That is universal set A, B. That is universal set A, B. Universal set A, B. Universal set A, B. Now, first is A difference B. A difference B. Then B difference A. Then the union of these two, A difference B, union B difference A. Second is A union B. Third is A intersection B. Then portion presenting A union B defines A intersection B. Now, if I try to shed them now, A difference B, element present in A, not in B. Element present B difference, element present in B, not in A. If we take the union of these two, I'll be getting A, this, this. Fine. Then A union B. Everything is there in A or B. A intersection B. Present in A union B, not in A intersection B. That is, this portion is excluded from there. I get this, not the intersection B portion again. And I find the third diagram and the sixth diagram are identical, hence these two sets are equal. Clear? And that is what is by which we don't do in the case of the Venn diagram. Now let us see how do we get, with the help of the laws of algebra of sets. Can I have it?
Yes, sir.
Okay. I'll start with left-hand side. A difference B, union B difference A. I want your support so that this is A intersection B complement, union B intersection A complement. Which law I have used? Can you recall? Which law I have used? You forgot. This is difference law. This is A union B complement, union B intersection A intersection with, sorry, A intersection B complement union B, A intersection B complement union A complement. Can anyone tell me which law I have used? Take the set to be one, as if one set. Take the set as if it is one set. P union B intersection A complement. Then I distributive law. Those who are considering this to be a little difficult, please, I have done plenty of sums based on that. Please, when we take the next class, before that, at least practice those sums once more, because it happens, because you are out of practice for so many days. Here are also two different types of operation. We go for distributive law again. A intersection B complement union B, and A intersection B complement. Rather, I do it this way. A union B intersection B complement union B. Intersection. Again, this was distributive law. Again, this is A union A complement intersection B complement union A complement. Again, we go for distributive law. We go for distributive law. A union B, nothing to do. Intersection B union B complement or B complement union B. What is that? B complement union universal set xi. Intersection A union A complement xi. Intersection A complement union B complement. That is complement law. Complement law. Intersection xi, that is A union B only. Here, intersection A complement, intersection union B complement. Identity laws. Identity laws. Next, can anyone tell me what law I am using now? Which law? From this step to this step, which law I am using? I have not used anything in the first part. A union B remains as A union B. So what I have done in the second portion, what law I have used?
Sir, De Morgan's law.
De Morgan's law, very good. De Morgan's law, very good. And finally, this is equal to A union B intersection A intersection B. Which law I have used? P intersection Q complement, as if this is P difference Q.
Difference law.
Difference law. And that is to be done, that is to be proved, and it is proved. Difference law. Shall I give you one or two more sums like this?
Yes, sir.
Okay. I'm giving you two sums at a time. And you have to do with the help of both the methods, that is Venn diagram as well as law of algebra of sets. I have given you two sums. Okay, first one. I believe that with the help of the Venn diagram we can manage it. Do I have to do it with the help of the Venn diagram?
No, sir.
Okay, thank you. So by law of algebra of sets, LHS A difference B. Is it A intersection B complement? Which law? Which law?
Difference
Law.
Difference law. Is it going to B complement intersection A? Which law? I just interchange their position. Commutative. Commutative law. This is B complement intersection. A complement whole complement. A complement whole complement is A, which is common complement law. A set intersection some complement, B complement difference A complement, that is difference law. And we have put that. We have put that. Shall I rub it?
Yes.
Okay. The next one also, I believe that you can manage it with the help of Venn diagram. But how to do it with the help of the law of algebra of sets, LHS. A interest union B difference C. Nothing. I've just repeated that. This is equal to A union B intersection C complement. Which law should I write?
Difference law.
Difference law. This is A intersection C complement union B intersection C complement. Which law?
Distributive.
This is known as right distributive law, to be very specific. This is A difference C union B difference C, that is difference law. I'm going to prove that only. Now, what is my request to you is this. We have already done the set theory, and your job, before starting that set theory and up to say Cartesian product, which we have done today. So set theory, go through the set theory once more, because we have done it, and up to Cartesian product. So that in the next day, we entirely will be within the calculus part. Okay? So thank you so much. Stay safe and sound. Bye-bye.